When x coordinates in the dataset have irregular intervals, common methods that can be used are Newton's divided difference interpolation and Lagrange interpolation. Learn them here in numerical solutions to CE problems. If we have a dataset with the following points 0, 1, 1, 3, 3, 49, 4, 129, and 7, 813, h in this case jumps irregularly from 1, 2, then back to 1, and then 3. One method to interpolate is to use Newton's divided difference table, which eventually will help you interpolate through Newton's divided difference interpolation. The other method discussed here is Lagrange interpolation. Let's work with Newton's divided difference table first. This table is somehow similar with Newton's difference table, although because of the different h intervals, there should be a divisor. Note that the labels for each column of the changes in y this time is written differently, which actually helps you out understand which x values are included in the divisor. So we start with the first column on top, giving 3 minus 1 all over x values of 1 minus 0. The next is 49 minus 3 all over 3 minus 1. This is also followed by 129 minus 49 upon 4 minus 3. And then the last is 813 minus 129 all upon 7 minus 4. For the second column, we start with 23 minus 2, and this is divided by the x values with a single gap, that is 3 minus 0. Next is 80 minus 23 all over 4 minus 1. The last for the column is 228 minus 80 all over 7 minus 3. For the third column, we have 19 minus 7 all over 4 minus 0. These x values include two data point gaps noted from the x column. The other coefficient from this column is 37 minus 19 all over 7 minus 1. Then the converging coefficient has 3 minus 3 all over 7 minus 0, and it gives 0. With the table already filled up, which coefficients are we to use to interpolate f of 2.8? The standard trend of coefficients that we can use is the leading forward differences of 2, 7, 3, and 0. Using these includes the first x as x0, followed by the others. This time tagged as x1 for 1, x2 for 3, x3 for 4, and x4 for 7. Also note that the last coefficient under the fourth y-change column is 0. This means the fourth term is basically zeroed out or disregarded, making only 3 coefficients functional. Thus, if there are only 3 necessary terms, we can also work on the next trend below with 23, 19, and 3, where x0 is 1, x1 is 3, x2 is 4, and x3 is 7. With two alternatives with Newton's divided difference interpolation, we look for f of 2.8 starting with x0 as 0. This is the orange trend. Take out the coefficients from the table where x0 is 0. F of x0 is 1. The first difference is 2. The second coefficient is 7, followed by 3, and lastly by 0. These are the coefficients that will be plugged in the pattern equation as written, where each coefficient is multiplied by an iteration of x minus x naught, x minus x1, and so on. By plugging values, f of 2.8 starts with f of x naught, which is 1, plus 2.8 minus 0 times 2. The next term includes 2.8 minus 0 with 2.8 minus 1 and multiplied by the change 7. The third term has 2.8 minus 0 times 2.8 minus 1 and 2.8 minus 3 multiplied by 3. Then the last term has 2.8 minus 0, 2.8 minus 1, 2.8 minus 3, and 2.8 minus 4 multiplied by y of coefficient 0. The terms are simplified as 1 plus 5.6 plus 35.28 minus 3.024, giving f of 2.8 as 38.856. Let's validate the function of 2.8 when the trend taken is with x naught equal to 1. This is the purple trend. So the coefficients from the divided difference table are 3 for f of x naught, 23 for the first change, 19 for the second, and 3 for the third y difference. With the same pattern equation, we take f of 2.8 as 3 plus the second term taken as 2.8 minus 1 times 23. The third term has 2.8 minus 1 times 2.8 minus 3 times 19. And the fourth term is 2.8 minus 1, 2.8 minus 3, and 2.8 minus 4 multiplied by 3. The equation is then simplified as 3 plus 41.4 minus 6.84 plus 1.296, which can be reduced into 38.856 as the function of 2.8, exactly the same from the first trend. The next step is to validate the function through Lagrange interpolation. Since this method does not use a table, we only have the dataset to use. The number of data points will reflect the number of terms in the long computation. The first term is figured out by covering the first data point. F of 2.8 is then solved as a ratio of x values. The numerator will include the x required minus the x values in the dataset. That is 2.8 minus 1, 2.8 minus 3, 2.8 minus 4, and 2.8 minus 7. The denominator is also computed similarly, but instead of the required x, we use the covered x. So the denominator includes 0 minus 1, 0 minus 3, 0 minus 4, and 0 minus 7. Again, all values from this ratio are from x, which will then be multiplied by the covered y, which is 1. The second term is computed by covering the second data point. So the numerator has 2.8 minus 0, 2.8 minus 3, 2.8 minus 4, and 2.8 minus 7. The denominator comprises of 1 minus 0, 1 minus 3, 1 minus 4, and 1 minus 7. The ratio is also multiplied by the covered y, 3. Cover the next data point to have the third term with numerator of 2.8 minus 0, 2.8 minus 1, 2.8 minus 4, and 2.8 minus 7. The denominator uses the covered x of 3 minus 0, then 3 minus 1, 3 minus 4, and 3 minus 7. The multiplied y for the term is 49. The fourth term is then computed by covering the fourth data point. The numerator has 2.8 minus 0, 2.8 minus 1, 2.8 minus 3, and 2.8 minus 7. The terms in the denominator use the covered x of 4. So that would be 4 minus 0, 4 minus 1, 4 minus 3, and 4 minus 7. The y for this term is 129. Then cover the last data point for the last term. The numerator is then 2.8 minus 0, 2.8 minus 1, 2.8 minus 3, and 2.8 minus 4. The denominator uses the covered x of 7 minus 0, 7 minus 1, 7 minus 3, and 7 minus 4. The y included for this term is 813. Each term simplified as negative 0.0216, then 0.2352. Next is 51.8616, followed by negative 15.1704, then 1.9512. Adding all these simplifications gives f of 2.8 as 38.856, just the same.